Welcome to this. This is our 22nd lecture on the fundamentals of transport processes. We had started solving problems on transport in one dimension. Okay. If you recall, I had in the previous case posed for you diffusion problems for heat transfer in the bottom here, okay, for a surface, infinite plane surface heated from below. Okay. We had done a balance for an internal differential volume and got the diffusion equation for heat transfer. Okay. The same problem for mass transfer, we had posed it as a mass transfer problem, where initially the concentration is the same everywhere, and at time t is equal to 0, the concentration is instantaneously increased at the bottom surface alone. Okay. In that case as well, we had got a diffusion equation for mass transfer. And finally, for momentum transfer, what you have is a stationary fluid, and at time t is equal to 0, the bottom surface is moved with a constant velocity u, and that was a momentum transfer problem. The formulation was slightly different. Rate of change of momentum is equal to the sum of applied forces. However, the equation that we got was exactly the same as heat and mass transfer, except that the variable now was the velocity or the momentum density, and the diffusion coefficient was the diffusion coefficient for momentum diffusion. The force, instead of the sources, we had a body force in the x direction, okay, in the direction of momentum. The only difference was to keep in mind is that the shear stress now contains two indices. One is the direction of momentum itself. After all, momentum is a vector. The second is the direction across which there is transport, okay, or the direction perpendicular to the surface, okay, across which momentum is transported. So, this heat transfer problem, we had tried to get a solution. Okay. The original equation looks like this. We had neglected sources in this case, assumed that there are no sources. We had scaled the equations using a scaling for the temperature, so that in the transformed temperature, the temperature varies from 1 at the bottom to 0 far away from the surface. This is always advantageous, because the temperature profile expressed in terms of the original temperature varies between T naught and T infinity. So, that profile will change. Temperature profile expressed in terms of the transformed coordinate varies from 1 to 0, and that will not change regardless of the problem that you solve. Okay. So, though we managed to scale the temperature, we could not find scales for the length or the time, because as far as the spatial coordinates are concerned, the plane is infinite in extent and the fluid is also infinite. So, we were not able to find a coordinate, a dimension to scale the length by. Similarly, the heating starts at t is equal to 0 and continues for all time, t going to infinity. So, we were not able to find scaling for the time either. There was a deficit of dimensional quantities with which we could scale the spatial dimension and time, and the only parameter in the problem is this thermal diffusion coefficient alpha, okay. And therefore, we could find only one dimensionless independent parameter, a combination of the spatial and the time dimensions, which was this parameter psi, okay, z by square root of alpha t. Okay. This was the only dimensionless coordinate that we could find. This is what is called a similarity transform, reducing from two independent variables to one independent variables, because there is a deficit in the number of dimensional parameters you can use for scaling the problem. Okay. So, we had expressed the temperature in terms of psi alone, okay, put it into this equation, and the final equation that we get is only a function of psi. It does not depend individually on z and t. Okay. We had also scaled the boundary conditions, okay, expressed those boundary conditions in terms of psi, and we had found that two of these boundary conditions one initial condition, the other boundary condition far from the surface, when expressed in terms of psi, reduced to just one condition. Okay. That is required because what we have finally is a second order differential equation in psi, and we should get only two boundary conditions in psi. Okay. So, next let us proceed to solve this problem. Okay. The equation that I have is that d square t by d psi square is equal to okay, and the boundary conditions are at t star is equal to 1, okay. So, those are the equations and the boundary conditions. Okay. This can be solved quite easily. Okay. You just write dt by d psi is equal to some parameter w, okay, the derivative. Okay. Therefore, dw by d psi is equal to minus psi by 2 w. Okay. If you integrate this one, you will get log w is equal to minus psi square by 4 plus some constant a. Okay. Therefore, w can be written as, okay, let us call this constant as a prime. Okay. W can be written as a e power minus psi square by 4, okay, and this is equal to d star by d psi, okay, which means that t star is equal to some constant b plus a integral. Okay. Note that I have to integrate psi, so I have to use a dummy variable, okay, from 0 to psi d psi prime e power minus psi prime square by 4. Okay. So, this is the solution. Okay, so, let me just remove this here to avoid confusion. Okay, so, that is the solution. Okay. Boundary conditions: at psi is equal to 0, t star is equal to 1. Okay. Therefore, this implies that b equals 1. Okay. As psi goes to infinity, t star is equal to 0. This means that b plus a integral 0 to infinity is equal to 0. Okay. This integral you cannot express it analytically further. Okay. It's a Gaussian integral, so you cannot express it analytically further. It is what is called an error function. Okay. However, you can get this one. Okay. Okay. This integral 0 to infinity d psi prime e power minus psi prime square by 4 is just equal to square root of pi. Okay. So, using that we know that b is equal to 1. Okay. So, therefore, the final expression for t star becomes equal to 1 minus 1 over root pi integral 0 to psi d psi prime e power minus psi prime square by 4. Okay. So, that is the final solution for t star. Okay. And rather than writing it as psi, I can write this in terms of the original variable z by root dt. Okay. I can write this in terms of the once again I should write it in terms of the thermal diffusivity alpha, okay, z by root alpha t. Okay. So, that is the final expression for t star. Okay. Now, we had earlier assumed that the fluid was infinite. Okay. You can ask the question, when does that approximation break down? Okay. So, so let us first look at the approximations that we have made while solving this problem. Okay. In this case, a practical application will have a finite fluid. However, we have assumed in this case that the fluid is of infinite extent. Okay. Real fluids will always have some height and some area in the x direction. Okay. When is that infinite fluid approximation valid? In other words, what is the distance over which the fluid, the temperature due to the bottom has penetrated into the fluid? Okay. That is obvious here. Okay. The similarity solutions depends only upon this variable z. Okay. Therefore, if I were to express the similarity, the temperature in terms of the variable psi, okay, at all times I am going to get a universal curve, okay, T star as a function of psi. Okay. This curve is going to be independent of time. Okay. It goes from 1 to 0. Okay. This curve is going to be independent of time. It is given by this functional form. Okay. However, if I were to express this in terms of z, okay, I would get different curves. This once again has to go from 1 to 0 far away. Okay. However, at early times it would basically be a step function. Then as time progresses, okay, this depth over which this temperature field penetrates would be small. Okay. And then as time further progresses, this would increase and increase further. How does it increase? It is obvious from this functional form. Okay. This penetration depth, okay, of the temperature field, okay, this length scale L over which the temperature has penetrated, L has obviously got to be proportional to square root of alpha T. Okay. Okay, it has to be proportional to square root of alpha T. Okay. It is obvious from here. What this is saying is that if I had different values of z and different time intervals, the temperature at each of those would be the same. Okay. So, if I had different values of z and different time intervals, okay, so long as square z by root alpha T is the same, the temperature is the same at all of these locations, even though z may change, T may change. So long as z by root alpha T is a constant, the temperature is a constant. Okay. Now, the temperature field actually decays, okay, it decays pretty quickly actually. Okay. If I actually plot this temperature field, okay, 1, 2, 3, 4, 5 and so on, this decays to very close to 0 by the time you reach a distance of about 4, when psi is equal to 4 from the surface. You reach more or less 99%, okay, of the temperature reduces to about 1% of its original value, okay, within about psi is equal to 4. Okay. So, the penetration depth is basically some constant times square root of alpha T, okay, and this increases proportional to T to the half. Okay. So long as my system size, okay, so long as my system size L is much larger than root alpha T, I can assume that the fluid is an infinite fluid. Okay. Once L becomes comparable to alpha T, then this approximation is no longer valid. Okay. Okay. This is infinite fluid. Okay. When L becomes comparable to root alpha T, or T scales as L square by alpha. Okay. Alpha is a thermal diffusion coefficient. It has dimensions of length square per time. So, if you take L square by alpha, you get a time. Okay. So, for time small compared to this thermal diffusion time across a length L, okay, for time small compared to the thermal diffusion time across this length L, okay, you can consider the fluid to be infinite. Once the time becomes comparable to the thermal diffusion time, you can no longer consider the fluid to be infinite, and the fact that there is an upper boundary does matter. Okay. And that thermal diffusion time, okay, just from dimensional analysis has to scale as length square by the thermal diffusion coefficient. Okay. Okay, this is just a simple scaling. Okay. Good. So, now we have looked at under what conditions this approximation is valid. Okay. Obviously, this approximation is valid so long as the length scale is the time of heating is small compared to the thermal diffusion time across the height of the container. Once it becomes comparable, you no longer can assume that the fluid is infinite. Okay. So, next thing, how do we calculate the fluxes in this case, for example? Okay. So, I have the temperature field T star is equal to 1 minus integral 0 to z by root alpha t. Okay. D psi prime by 4. Okay. So, that is the final expression of temperature. What is the heat flux coming from the surface? Okay. Qz is equal to minus k dt by dz at z is equal to 0. Okay. That is the thermal flux, total heat energy coming out from the surface. Okay. I can express this in terms of T star. Okay. After all, we know that T star is equal to T minus T infinity by T naught minus T infinity. Okay. So, dt by dz will just be equal to minus k T naught minus T infinity d T star by dz. Okay. Now, I have to use the substitution that psi is equal to z by root alpha t. So, if I use that substitution, okay, this is at z equals 0, I can write this as minus k into T naught minus T infinity by root of alpha t, okay, partial T star by partial psi at psi is equal to 0. Okay. Because when I take the derivative with respect to psi, I just get one factor of 1 over root alpha t coming out. Okay. And what is the value of dt star by t psi at psi is equal to 0? This is the value of T star. Okay. If I take one derivative, okay, the derivative of the first term here 1 is just equal to 0. The derivative of the second term is an integral from 0 to z. Okay. Therefore, the derivative of the second term is just equal to the value of the integrand. Okay. The derivative of the second term is just equal to the value of the integrand, what is within the integral. Okay. You are taking the derivative of an integral, you just get the integrand alone. Okay. So, this is equal to times minus 1 by root pi, okay, into the value of the integrand in this case is just equal to e power minus psi square by 4 at psi is equal to 0. Okay. This is just equal to 1, okay, at psi square at psi is equal to 0, exponential of minus psi square by 4 is just 1. Okay. So, I basically get k by root of pi alpha t. Okay. So, that is going to be the heat flux coming from the surface. So, the heat flux decreases with time as 1 over square root of t. Okay. That is no surprise. The penetration depth increases proportional to square root of t. The heat flux is the derivative. So, derivative will scale as the temperature difference divided by the characteristic length scale. Therefore, it decreases 1 over square root of t. Okay, from the surface. You can also find out what is the total heat that is coming out up to a certain time. Okay. How much heat has come out of the fluid, okay, up to a certain time, okay, due to this heating. Okay. That should be the amount of heat that you have to supply at the bottom, okay, due to this heating. Okay. So, how much heat has come out? Q will be equal to integral from 0 to t dt prime qz at t prime. Okay. And you can do this integral quite easily. You will get basically k into t naught minus t infinity by root of pi alpha integral dt prime 1 by root t prime, okay, from 0 to t. Okay. So, this will turn out to be equal to k, when I do the integral of 1 over root t, I get square root of t divided by a half. So, if I get a factor of 2 there, okay. So, I will get 2 k t naught minus t infinity square root of t, okay, divided by root of pi times alpha. Okay. So, that is the total amount of energy that has emerged from the surface up to a time t, okay, and that scales as the square root of t, okay. As time progresses, that scales as the square root of t. Okay. The other issue here is that in all of these cases, okay, I had solved the problem for heat transfer. Okay. Partial z square. Okay. This equation where t star is equal to t minus t infinity by t naught minus t infinity. Okay. And the solution was t star is equal to 1 minus 1 by root pi, okay, integral 0 to z by root alpha t d psi prime e power minus psi prime square by 4. That was the solution. Okay. I had also posed for you a problem of mass transfer. Okay. This was a problem of mass transfer. C is equal to C naught at the surface, C infinity far away. At time t is equal to 0, you impose the concentration is a constant C infinity everywhere, and you imposed a different concentration at the surface C naught. Therefore, diffusion takes place. Okay. Equation was exactly the same. Therefore, the solution that I get will also be exactly of the same form. Okay. Partial C star by partial T is now thermal mass diffusivity partial square C star by partial Z square, okay, with C star is equal to C minus C infinity by C naught minus C infinity. Okay. If I pose it this way, C star is equal to 1 minus 1 by root pi integral 0 to z by now root dt. I substitute the mass diffusivity for the thermal diffusivity d psi prime e power minus psi prime square by 4. Okay. Exact same solution. Okay. Similarly, I could solve the momentum transport problem as well. Okay. In this case, we are looking at the transport of momentum, okay, x momentum in the z direction. The equation that I ended up with was exactly the same. Okay. The equation that I ended up with was exactly the same. In this, therefore, for this equation, the solution will once again be exactly the same. Okay. My equation will be of the form partial u x star by partial t is equal to nu partial square u x star by partial z square. Okay. U x star will just be equal to u x by u. Note that the velocity u infinity was equal to 0 because the fluid was stationary. Okay. And the solution for that will be equal to 1 minus 1 over root pi integral 0 to z by root of now kinematic viscosity times t. Okay. So, this shows the analogy between heat, mass and momentum transfer in this simple case where we use similarity transforms. I have tried to convey to you that there is a diffusion time scale, okay, or a diffusion length scale. Okay. The diffusion time scale is basically comes out of the kinematic viscosity, the mass diffusivity or thermal diffusivity. Okay. And when this diffusion time scale, okay, is small, okay, you can actually assume that the fluid is infinite. When it becomes when the length scale becomes comparable to the system size, you can no longer assume that this is an infinite fluid, and you have to actually solve the problem that takes into account the upper surface. Okay. This has seemed an idealized problem, okay, but however it does have practical applications. I had told you earlier that I will show you one particular practical application where this can actually give us a correlation for the Sherwood number for the concentration field. The when I solved this problem in terms of the mass concentration, it seemed a rather idealized problem, but I told you that I will solve one problem where I will actually calculate a correlation, okay, for the mass transfer. And that problem is mass transfer in a falling film. Okay. This is an industrial process. Okay. So, what happens is that you have some wall, okay, along which you have a fluid that is flowing downwards. Okay. The fluid is flowing downwards with some particular velocity field. Okay. These are operations called scrubbers, which try to reduce the poisonous gases in exhausts. Okay. So, you have a gas flow upward here, okay, and you have a fluid flow flowing downwards. Okay. So, let me just draw this a little bit better for you. You will basically have this wall here, okay, and the fluid will actually come in through a weir on top. Okay. Fluid will actually come in and then it will flow as a film down, okay, a film of some thickness T. Okay. Okay. And as the fluid is flowing downwards, there is going to be mass diffusion of the species that you want to remove, okay, across this interface. And we can assume that the concentration in the gas is a constant, okay, whereas the concentration in the liquid, okay, is less than the solubility, and because of that you have a mass flux across. Okay. So, therefore, we have a situation where the concentration at the surface of this gas is some value Cs, and into the liquid this concentration C is equal to 0. Okay. And there is mass diffusion across. Okay. This mass diffusion takes place over some length scale L. Okay. This is the length scale over which there is diffusion that is taking place across the interface, and the fluid is moving downwards with some velocity profile u. Okay. Now, this problem we can idealize it as the flow in an infinite film of fluid, provided the penetration depth of the gas, okay, within this fluid is much smaller than the total thickness. Okay. In that case, it looks like the flow through an infinite fluid. Okay. And we can also idealize it as a time dependent problem if we consider a parcel of fluid as it moves downwards. Okay. If you consider each individual differential volume of fluid as it is moving downwards and gas is diffusing in. Okay. So, rather than following the progression in the coordinate, we can just follow the progression of this particular element in time. Okay. And so, that is the idealization. Okay. So, I will show you in the next lecture how this can give us an actual correlation for the mass transfer coefficient or the Sherwood number, okay, using the similarity transform that we had used earlier in solving the flow in infinite fluid. Okay. So, this little bit we will continue in the next lecture. Okay. I will see you then, and after this we will look at some other problems where we can use similarity solution. I will see you in the next lecture.